Let's now look at a few examples of the types of calculations we'll be doing with that equation F equals IL cross B. So we will have some wires and some magnetic fields. My magnetic field is going to the right. I've got a wire that extends past the magnetic field, but we can ignore that. The segment of the wire that is in the magnetic field is 12 centimeters. We have a current flowing up the wire, and the angle between the wire and the magnetic field is 60 degrees, and we want to know the magnitude of the force on the wire. So if we don't care about direction, we can just use the magnitude form of that equation, which is ILB sine theta, and we're essentially just plugging in numbers. This one is pretty basic. We have a current of 30 amps. We've got a length of 12 centimeters. We need to make sure and convert that to meters, so 0.12, and we have a magnetic field of 0.9 teslas, and our angle is 60 degrees, so you plug that guy in and you get 2.81 newtons of force on that wire. And you can use a right hand rule if you want to do the direction, so you'd point your fingers along the wire, rotate your palm to the right, so you'd be feeling a force off in this direction. Not that it asked that, but just in case you were wondering. Next example, here we have a rectangle of wire, and only a portion of it is in a magnetic field. By the way, there's this other convention you need to be familiar with. If you have dots, so going left and right is easy enough. You just draw arrows to the right or arrows to the left to indicate the direction of the magnetic field. But if it's going into the page or out of the page, and a lot of times now that we're dealing with cross products, we're going to have to take into account all three directions. Going into the page, we draw with X's, and coming out of the page, we draw with dots. And the common convention to remember this is if you think about an arrow, like an old-fashioned arrow that you fire out of bow and arrow. I guess they're not so old-fashioned, but anyway, if the arrow is coming at you, you see the point of the arrow, which is kind of like a dot. And if the arrow is going away from you, you see the feathers, or fletchings, I believe they're called, on the back of the arrow. So then that would tell you that it's going away from you or into the page. Anyway, all of that is just to say that these dots are telling us that the magnetic field is coming toward the viewer out of the page. So this is actually one way that you can measure the magnitude of a magnetic field, is by having a situation like this where you hook this up to some force meter and find the force pulling on this. So before we start filling in numbers, let's think about conceptually what's going on. If I have a downward current here, so point your fingers down, and a magnetic field coming out toward the viewer, so point your palm toward you, on this little segment of wire from here to here, you're going to have a force to the left. Over here, the current is going up, magnetic field is still coming out, so that will swap the directions and you have a force going to the right. Because this is kind of like a series circuit, there's no way for the current to go anywhere else. We know that the currents on the two sides have to be equal. The lengths are equal, so these two forces are going to be equal in magnitude and they'll cancel out. On the bottom segment here, we already see the direction of the force, but you can think about it real quick. The current is going to be going this way, so point your fingers that way, point your palm at yourself, and your thumb will be pointing down, which is the direction of the force. So in this case, we don't know the field, we know the force, because that's actually quite a bit easier to measure. And we can measure the current in the wire, and then if we measure the length of the wire, it gives us that somewhere. Here we are, 10 centimeters. Then we can go ahead and find the magnetic field from those measurements. Now if we think about the angle, my current is going directly to the right, my magnetic field is coming directly out of the screen, so that is a 90-degree angle. So we just end up with ILB, because really it's ILB sine of 90, and sine of 90 is 1. So there is the equation we're going to deal with, and then if we solve that guy for the magnetic field, it's F over IL. Go ahead and throw in your numbers, 3.48 times 10 to the negative second divided by 0.245, and the length is 10 centimeters, which is 0.1 meters. And this works out to be a magnetic field of 1.4 teslas. Okay, one more. This one is a little bit trickier. Here we've got a curved semicircular segment of a wire. Again, we've got the these segments here and here having equal forces in opposite directions, so there's no net force there. And now we just need to worry about this curved segment here. We have the x's, which tells us that it's going away from the viewer or into the page or the screen in this case. And we want to find the net force acting on the wire. If we think about the forces acting on each segment, you point your finger in the direction of the wire, so tangent to the wire essentially, and then your palm is going to be down, so you're going to have forces coming perpendicularly out from this wire along all of the segments. And so because of symmetry, every force to the left is going to have a force to the right. Even these ones that are at an angle, the component that's to the left is going to have an equal component to the right. So the net force is going to be only in the vertical direction. All the horizontal forces are going to cancel out. So the total force, we can say, is just the vertical component of the force. And to find that vertical component, we are going to have to do an integral of all of the little forces on each segment of the wire. And since we just want the vertical component, we're going to do a sine of the angle phi here. This is not theta. Theta is the angle between the current and the magnetic field. This angle here is phi, which is a different angle. Okay, and then we can go ahead and plug in ILB sine theta for our force equation, except for the L part. That's what we've divided up into infinitesimal segments. So I'm going to write this as I, and they call the magnetic field B naught, so we're going to go ahead and use that. And then we've got a sine theta from our general equation, and then we keep this sine phi as well, and then we're going to put a dl here. So our L became a dl because we chopped it up into little segments. Now again, as we saw in the previous example, our current is going in the plane of the page at all points. Even though it changes direction, it's always in the plane of the page or the screen. And the magnetic field is always going directly into the screen. And so that is always going to be a 90-degree angle. So theta is actually constant, and it's 90. So this guy becomes a 1, and essentially goes away. And we can pull out the constants. The I and the B naught are constant. So we've got that, and now we've got the integral of sine phi dl. So we have to either substitute one or the other so that we have the same variables going on here. And we can say that dl is equal to r d phi, because that's the definition of how an arc length compares to the angle subtended, right? This is just saying that L equals r theta, but we're chopping it up into little pieces, and it's not theta, it's phi. Anyway, so we can go ahead and make that substitution in. The r is constant, so that can come out front and join the constant party out there. And we've got sine of phi d phi, and then our limits are going to be from 0 to pi, and we can perform that integral. So I b naught r, the integral of sine is going to be negative cosine, and then we're going to have cosine of pi minus cosine of 0. Cosine of 0 is 1, cosine of pi is negative 1, so we're going to have negative 1 minus 1, which is going to give us a negative 2, and then we've got a negative sign over here. This was being multiplied. Double bracket this guy up. It wasn't being subtracted. So anyway, those negatives go away, and you end up with a 2I b naught r is the force on that wire, which interestingly enough is equal to the force on a straight wire of this length, because that's 2r. That's all for now. See you in class.